we're going to continue on with our discussion of Chapter 17. In Section 5, we deal with the idea of electric fields. Now, when we talked about Coulomb's law, we discussed the fact that any two charges feel a force between them. But the question is, how do two charges that are in empty space even know the other charge is there? How do they interact? And Michael Faraday developed the idea of an electric field to explain this interaction. His theory was that every electric charge is surrounded by an electric field, and it's this field that exerts forces on other charges. So let's suppose that we have a positive charge here. We'll make a rather large positive charge. I know that if I have another positive charge over here, and I'm going to let this one be a little bit smaller, I'll call it Q prime. This is a big charge. If it's also positive, it's going to feel a force directed away from this charge. If I were to bring it in closer, maybe bring it down here, that same positive charge would feel an even larger force because it's closer. If I bring it up here, it'll be kind of medium, but in each case, a positive test charge is going to feel a force directed away from this positive charge. The electric field is actually defined as, in this system, that the electric field at some given point is equal to the force the charge feels divided by the magnitude of the charge. We measure it in units of newtons per coulomb. So if at a particular point, I'm going to look at this point right here, I'm going to call that point P. If the electric field at point P is 500 newtons per coulomb, that means a 1 coulomb charge would feel 500 newtons of force. A 2 coulomb charge would actually feel 1,000 newtons of force because it's 500 newtons per coulomb. Now, if I come to this location, that electric field is going to be bigger than 500 newtons per coulomb. It's going to be stronger, right? The closer I get, the stronger that electric field is going to be, okay? Electric fields are vector fields. Whoops. What does it mean if something's a vector field? It means that field has direction, and the direction matters. In particular, the electric field points in the direction of force on a positive charge. What's that mean? It means if the electric field points to the right, as it does right here, point P, a positive charge feels a force to the right. A negative charge would feel a force to the left. So, and that's always true. If a positive charge is feeling a force in one direction, then a negative charge is going to feel a force in exactly the opposite direction. As a result of this, one thing we know is that the electric field always points away from positive charges and toward negative charges. That makes sense. We would expect that would be the direction of the force on a positive charge. Positive charge always feels a force away from other positive charges, and it always feels a force towards negative charges. Now, if there is an electric field inside a conductor, there's our symbol for an electric field, inside a conductor. So let's suppose we have a ball of metal or something. The result is it would cause charges to move. In electrostatic conditions, if you'll remember, that means there's no moving charges. The electric field inside a conductor must be zero. So if you think about this, let's suppose that I have a solid conductor with excess positive charge. What's going to happen is that positive charge is going to try to get as far away from each other as possible. They're going to exert forces on each other. And the way they're going to get as far away from each other as possible is that excess charge will all end up on the surface of the conductor, evenly spaced out, evenly distributed. Inside the conductor, the electric field is zero. None of the charges that are inside of the conductor are going to feel a force. Everything is going to be in a case of static equilibrium. If we have a region of space where the magnitude and direction of the field are constant, we have a uniform electric field. Let's think for a minute. If we had a point charge, we can see that with a point charge, I'll let it be a positive point charge, the field is strong here when we're close to it and weak as we get farther away. Okay, that's not a good example of a uniform electric field because, like I say, right here the field's very strong, you feel a really big force, but when you're farther away, you feel less force. And notice here the force is in two totally different directions and different sizes. That's real typical. A lot of times electric fields are not uniform. However, it is possible to get a fairly uniform electric field. Uniform electric fields generally are made using parallel plates. If I have one parallel plate that has a positive charge on it, and I have a second parallel plate that has a negative charge on it, we know electric field lines are going, if you're a proton, you're going to feel a force away from positive towards negative. Let's draw those in a different color. Let's draw our electric field lines in blue. Then our electric field's going to point like this. Whoops. Why is my, there we go. And they're going to be nice and fairly uniform. We haven't really talked about drawing field lines yet, but the electric field line pretty much everywhere inside these plates is going to point straight down from positive towards negative. Now, when you get close to the edges, you start to get some bowing, and we start to see we don't have a perfectly uniform electric field anymore. But really, as long as we're here in the middle, we get a really nice uniform electric field. All right, let's think about an example. It says an electron is shot horizontally into a uniform electric field that points straight down. Well, that's exactly what I just drew. I drew in a uniform electric field that points straight down. Suppose we have a little electron and it gets shot in here. It's going like this. And we know it's got a negative charge. We shoot that little electron in there horizontally. In what direction will it accelerate? Well, let's think. The acceleration is going to be in the direction of the force. If you have an electric field that points down and negative charge, will feel an upward force. The field points down, but the electron will feel a force upward. If the direction of the force is up, then the direction of the acceleration is up. Why? Newton's second law. The net force is mass times acceleration, and they point in the same direction. So rather than when you shoot this negative charge, it'll curve. It'll feel that upward force and will bend towards that plate. And that's exactly what we would expect to see. Okay, so we're moving into section 17.6, which is really just a continuation of this idea of electric fields. I'm going to begin with the principle of superposition. And we've had principles of superposition when we talked about waves earlier. When we're talking about the electric field, all this principle says is that the electric field, due to two or more point charges, is the vector sum of the individual fields. Okay, well, let's think about for a point charge how we can do this. We know that the definition of the electric field is the force divided by some test charge. But if we think back to Coulomb's law, the force is equal to K, absolute value of Q times Q prime, there's our two charges, divided by the distance squared. If I divide by Q prime, I end up getting that for a point charge, the magnitude of the electric field, this doesn't give us direction, is just this force divided by Q prime, so it's K, absolute value of the charge, divided by R squared, okay? We know that the direction is going to be outward in all directions from a positive charge and towards a negative charge. One of the ways that we represent electric fields that's really helpful is to use electric field lines. Now, electric field lines are discussed more in section 17.7, but I think it's so valuable. Let's look at a picture. So if I have a positive test charge, the electric field can be represented by lines that point in the direction of the field, which in this case is outward. I can't draw in 3D. If I could, it would be, you would see them coming spherically in all directions. But it would look like this. Notice when you're close, the field lines are closer together when you're close to that charge. As you get farther away, that electric field is an inverse square law. It reduces as 1 over r squared. Now, if we had a negative charge, the difference is our electric field lines now would point towards the negative because we know a positive charge would be attracted towards this negative charge. And again, keep in mind that realistically, this should be three-dimensional, but of course I don't have a way to draw in 3 dimensions. Let's do an example. Find the electric field strength. I don't care about the magnitude, but I want to know how strong it is due to a proton (5.29 times 10 to the negative 11 meters from it. That 5.29 times 10 to the negative 11, that's the Bohr radius. This is from the Bohr model of a hydrogen atom. Remember, a hydrogen atom is really simple. It's got one little proton and it's got one little negative electron. And this distance here is what we call the Bohr radius. Now, we know that that electron can be found anywhere surrounding it in an electron cloud, but that distance, oh, and I wrote the wrong distance. Let me fix that real quick. That distance of 5.29 times 10 to the negative 11 is the most likely place to find it. So we would say that our electric field strength is K, absolute value of Q, over R squared. So this is 8.99 times 10 to the 9th. That's Coulomb's constant. Q for a proton is just a charge on a proton or electron. It's 1.60 times 10 to the negative 19 coulombs. And then that Bohr radius, 5.29 times 10 to the negative 11 squared. I'm going to put that in a calculator, and I'll find that the electric field strength is 5.14 times 10 to the 11th newtons per coulomb. That's a pretty strong electric field. Of course, they're very close together. That's an 11. That's a big number. Let's do another example, or no, a continuation of an example. Well, really, it is another one. Let's find the electric field. Strength, and again, I'm not worried about direction, just magnitude, of a Van de Graaff generator. Those are those big spheres that somebody puts their hand on and it makes their hair stand up on the end. If the sphere has a radius of 0.50 meters, that's a pretty big Van de Graaff generator. And has a charge of 1 microcoulomb at a distance of 1 meter from its center. Let's draw a picture. So your Van de Graaff, your basic Van de Graaff generator looks like a big metal sphere. And then inside here, it's going to stand, there's a belt. And that belt generates a static charge. So they're telling us, here's the center. This has a radius of 0.5 meters, and they're wanting to know the strength of the electric field out here, a distance 1 meter from the center, so this would be another 0.50 meters. Well, interestingly enough, you can treat a charged sphere as if all of the charge is concentrated at its center. So really this part doesn't even matter. We just know that we are a meter away from the center of charge. So in that case, our electric field, I don't need the arrow because I'm just doing the magnitude, I'm not doing the direction. The electric field strength is again KQ over R squared. So we have 8.99 times 10 to the 9th, there's K. Our charge is 1 microcoulomb. Micro is -6. And of course, 1 meter squared. We don't even really need a calculator for this. It's going to be 8.99. 9 and -6 is going to be 3. One squared, of course, is just 1. This is newtons per coulomb. Or if you wanted to write it out, 8,990 newtons per coulomb. It's strong. It's not nearly as strong as the electric field inside that hydrogen atom, where the distance was so small. All right, let's look at another example. This example, we're going to look at an electric dipole. Basically, this means we have two equal but opposite charges. And we're going to find the strength of the electric field at various different locations. So I'll try to draw this as neatly as I can. This is like the x-axis. Here is a point A that's going to be exactly in between the two charges. We'll put Q1 here. Q1 happens to be a positive charge. And we're going to put Q2 here. Q2 is equal, but it's negative. Going to run a vertical axis. Ooh, see if I can do it like this. There's my vertical axis. And again, little rough on my drawing on the whiteboard. And we're going to put a few other places. So this point right here, that's point B. This is located at 5 centimeters. This one's located with 4 centimeters between these 2 points. This one's also at 5 centimeters. Let's write down what they tell me. Q1 is positive 12 nanocoulombs. Nano is 10 to the negative 9 coulombs. Q2 is negative 12 nanocoulombs. The distance between the two charges, that's R, is 10 centimeters. If we write that out, that's 0.010 meters. And of course, A is at that halfway point. Okay, there's also a couple more points. There is a point C up above and D down below, but they don't give us distances. They're just going to ask us about direction there. So, first question says, find the electric field strength at A. Okay, it's just the vector sum of the two individual electric fields. So let's just do the electric field at point A for charge 1 is KQ over R squared. So there's K. And again, this is an absolute value. We just need to know the sign. So Q was 12 nanocoulombs. And then the distance, 0.005 meters. I think I accidentally changed my problem. Let me go fix it so it's like what it was in your notes. This was, let's see. Oh, I didn't change the problem. I just wrote something wrong here. 10 centimeters, 0.10 meters. And therefore, half of that, here we go, 0.05 meters squared. So, sorry, I kind of changed the problem a little bit. So there's our problem. We've got things labeled right, 5 centimeters, 0.05. And if we put that in, we see that that is going to come out to be 4.3 times 10 to the fourth, and that's newtons per coulomb. And that is directed, well now here we have to do a little bit of thinking. If I'm Q1, I'm going to feel my electric field at point A is to the right because a positive charge placed right here at point A will feel a force to the right. So we want to make sure we get that direction. All right, the electric field due to charge 2, okay, Q2, absolute value. Notice the numbers are identical. It's going to also come out to be 4.3 times 10 to the fourth newtons per coulomb. Okay, this is a negative charge, so if I'm a positive charge located at point A, I will be attracted. So it is also to the right. So the total charge, the electric field strength at that point is just the sum. They point in the same direction, so we can simply add them together. If they pointed in different directions, we'd have to use vector addition. So our answer is 8.6 times 10 to the fourth newtons per coulomb to the right. Okay, we're going to keep our picture, but we're going to change the question. So I'm going to erase this. And let's find it at a different point. In fact, let's find it at B. Get this all cleaned up. Thought it would be easier to erase than to start over on the next page. So we want to find it at B. Okay, well now you can see Q1 and Q2 are going to definitely have different electric fields at point B. The electric field due to charge 1 will be pretty strong because B is pretty close. It's going to be pretty weak for charge 2 because it's pretty far away. So for charge 1, the electric field is K, Q over R squared. Sorry, I'm getting a little crooked. So 8.99 times 10 to the 9th times Q, 12 nanocoulombs, divided by I. This is a distance of 4 centimeters from Q1, so 0.04 squared. If I get my calculator and I type that in, I'm going to type it in right now to make sure I get 8.99 times 10 to the 9th times 12 times 10 to the negative 9, all divided by 0.04 squared. And that comes out to be, and I'm going to keep an extra digit or so because this is not going to be quite as simple, 6.74 times, 74 times 10 to the 4th newtons per coulomb. So a little bit stronger because it's closer. Okay. Now, for the second one, oh, in what direction? Well, let's think. If I'm a positive charge and I'm at point B, I am repulsed by this. It's going to be to the left. Remember, it's going to point away from this positive charge. So if I'm at B, I'm going to feel a force to the left. Now, the second part, let's do for the other one, same formula, but this time we have a different distance. Still 12 nanocoulombs. But this time the distance between Q2 and B is actually 14 centimeters. 14 centimeters, 0.14 squared. And that's going to come out to be about 5.5 times 10 to the 3rd newtons per coulomb. A lot weaker, you can see. And let's think, if you're a positive charge, you'll be attracted to Q2, so that's actually to the right. Okay, so if I'm sitting right here and I'm a positive charge, I'm being pushed to the left by Q1, but I'm being pulled to the right by Q2. So the total electric field is going to be, if we go with our signs, a negative 6.74 times 10 to the negative, or 10 to the 4th, and a positive 5.5 times 10 to the 3rd. So if I add those negative 6.74 times 10 to the 4th plus 5.5. Oh, that was actually, there was an extra place there. I didn't, times 10 to the 3rd. And my answer came out to be negative 6.19 times 10 to the fourth, or with two significant digits, I'm getting 6.2 times 10 to the fourth newtons per coulomb to the left. So I just did a vector sum of the two forces. The stronger force was exerted by Q1, it was to the left. The weaker force from Q2 was to the right. Okay, the last part of this question simply asks about what is the direction of the electric field at point C? Well, think about that. Let's do common sense. So I am going to go ahead and draw another picture. So there's this. Here's point C. Here's point D. Here's our positive Q. Here's our negative Q. Odd. We want to know the direction of the electric field. All we have to do is think, if I put a positive charge here, it would feel F1 would push it that way. That's the force coming from here. And this is Q1, this is Q2. F2 would be towards this. So F2 would be this direction. The vector sum, remember, these are equal charges, so these are equal forces. So the answer is the force at C is to the right. What does that tell me? That tells me that the electric field points right at point C. If we come down here to point D, again, a charge here will feel a force this way due to Q1. It'll be repulsed, but it will feel a force this way due to Q2. And again, when you add those up, the net force is going to be to the right. So E points to the right at D. Just think about the individual forces and then think, what would be the direction of that vector sum? All right, let's move on to section 17.7, and it deals with how do you draw electric field lines. I want to start by saying that electric fields are real. Electric field lines are not real. They don't actually exist. But electric field lines give us a way to visualize the strength of an electric field. All right, so here's some rules about electric field lines. Electric field vectors are tangent to electric field lines at any point. Second, the electric field lines are closer together. Where the field is stronger. And finally, electric field lines point away from positive charge and toward negative charge. Okay, so let's just look at some pictures. Suppose I have some point charge, and look at a point charge. Q. I have a positive point charge Q. I'm going to draw it here. There's my point charge. It's a big point. I know the electric field lines will point away from it in all directions. I usually draw 8 most of the time because it's easy to space out 8. Now, if I hover here, have a negative, but this is twice as much charge, negative 2Q, I indicate the fact that it's negative by drawing the electric field lines pointing in. But I also need the number of lines to be proportional to the charge. In other words, the electric field due to negative 2Q is twice as big in size as just the electric field due to Q. So since it's got twice as much charge, I'm going to have to go in and draw twice as many lines. And again, all of these will point towards the negative charge because a positive charge would feel an inward force towards that. If I draw the electric field lines for a dipole, remember that's where you have a positive and a negative charge. We have 2 charges. Obviously, in between is easy because a force would be away from the positive towards the negative. But the rest, think of adding what they look like separately and putting them together. So, normally a positive charge feels a force away. And normally a negative charge feels a force that points towards it. But what happens here is it would feel a force you would think up and away, but it also feels a force over. When we get finished, this may or may not remind you of something you've seen before. I don't know how many of you have ever looked at magnetic field lines by using like iron filings. That's the magnetic. This looks like the magnetic field lines. We haven't talked about magnets yet, of a bar magnet. That's probably one of the first indications that there's a real similarity between electrical forces and magnetic forces, and they're actually interconnected. And then finally, we can get a uniform electric field if we use parallel plate conductors. Again, we need 2 plates. I'm drawing them horizontally to save space, but they can often are drawn vertically. I think last time I let the top plate be positive, so I'll let the top plate be negative this time. This one will be positive, and you may say, well, how do you generate 2 equal oppositely charged plates? It's really simple. All you really need is a battery, 9 volts, and you hook the negative terminal to one plate, and you hook the positive terminal to the other plate, and you'll get oppositely charged plates. The electric field will always point away from positive toward negative. So my electric field lines, and again, I think I'll pick a different color. I should have done that earlier. So the electric field lines will point away from positive toward negative. We want to make them equally spaced to show that the field is uniform. It's not stronger one place than the other. At least not until you get over here. And over here, it gets a little wonky on the edges. But if we stay in the middle, we'll get a nice, uniform electric field. Okay, so that concludes sections 5, 6, and 7.